Hi class, this is the second video for chapter 4. So once you watch this video, that will conclude the lecture portion of chapter 4. So the next type of reaction that we're going to talk about are oxidation reduction reactions, or also called redox reactions. Many reactions are redox reactions. The biological reactions that take place in the cells of your body, a lot of those are redox reactions. Combustion reactions are also redox reactions. So let's go ahead and we'll define a few terms here, and then we'll get right into how to recognize an oxidation reduction reaction. We refer to oxidation numbers when trying to determine which of the substances in the reaction is oxidized or reduced. So the oxidation number, or the oxidation state of an atom, is the actual charge of an atom if it exists as a monatomic ion, or it's a hypothetical charge assigned to an atom in a molecule or a polyatomic ion, and we just follow some simple rules in order to determine those oxidation numbers. So it's a way of electron bookkeeping. So let's take a look at this reaction here. We dip an iron nail into a blue solution of copper 2 sulfate. What'll happen is, over time, the iron nail will become coated with metallic copper. And this is the reaction right here. We have solid iron in copper 2 sulfate solution, and the result is we have solid copper that deposits onto the nail, and we end up with iron 2 sulfate in solution. So the copper is actually displacing the iron. So this here is our net ionic equation for that. Again, we have the copper sulfate, which is completely dissociated, and here we have the iron 2 and then the solid copper. Obviously the sulfate ion is a spectator ion. Here's what's happened here. Let's take a look here. We have solid iron, and it has lost 2 electrons to form the iron 2 ion. And the copper ion has gained 2 electrons, and it becomes solid copper ion. So the electrons have been transferred from the iron to the copper 2 ion. Okay, so we say that iron has been oxidized and copper has been reduced. So oxidation is the loss of electrons. We can also look at it like this. It turns out that the oxidation number of any element in its elemental state is 0. So here we would have a 0 for the solid iron. And so the iron goes from 0 to +2. So we see an increase of oxidation number. Now, the copper, on the other hand, it goes from a +2 to 0. So the copper has gained electrons. Reduction is the gain of electrons, or we can look at it as a decrease in oxidation number. Now, how do we determine oxidation numbers? Here are some rules for determining oxidation numbers. For the atoms, In elemental form, the oxidation number is always 0. So for example, you can have molecular oxygen, hydrogen, solid copper, liquid mercury. The oxidation numbers for these would be 0. For example, here we have for phosphorus, for P4, the oxidation number would be 0. So oxidation numbers for an element or for an atom in its elemental form is always 0. Now, when we have a neutral compound, the sum of all the oxidation numbers is equal to 0. Okay, so I have sodium chloride. The sum of the oxidation numbers here has to be 0. For the atoms in an ion, for example, phosphate ion, the sum of the oxidation numbers for the atoms has got to be equal to the charge on the ion. Now, for ionic compounds, the oxidation number is just equal to the charge on that ion. So for example, group 1A metals, they're all going to have oxidation numbers of +1. Group 2A metals all have an oxidation number of +2. Group 3 metals, +3. Okay? Transition elements, whatever. So for example, here we have iron 3 chloride. The oxidation number on the iron would be a +3. It would be the same as its charge. Okay? Let's see. For nonmetals, for example, oxygen, it usually has an oxidation number of a -2 in most compounds. And that's in both ionic and molecular compounds. So the oxidation number is usually a -2. The one major exception is in compounds called peroxides, and those contain this ion. Okay, and this gives the oxygen, or each oxygen atom, an oxidation number of a -1. In compounds, the oxidation of fluorine is always a -1. In compounds, hydrogen usually has an oxidation number of a +1, except when it's combined with metals. These are called hydrides, and then it would have an oxidation number of a -1. But in most compounds, when it's bonded to nonmetals, the oxidation number of hydrogen is a +1. Okay? Nonmetals usually have negative oxidation numbers, but sometimes they can be positive. In binary compounds with metals, group 7A elements have a -1 oxidation number, group 6A a -2, group 5A a -3 oxidation number. When the halogens, remember the chlorate and the chlorite ions, then they can have positive oxidation states. And we'll take a look at that right now. So these rules, you need to know them. Okay, and they're also in your textbook. Make sure that you know those rules. So let's go ahead and assign oxidation numbers to each atom in the following compounds. So we look at this one. This is potassium oxide. It's ionic. And so we know the potassium has an oxidation number of a +1. The oxygen has an oxidation number of a -2. Notice that the oxidation numbers add up to 0. This is a neutral compound. So we have 2 potassiums, right? So each one has a +1 charge, and 1 -2 from the oxygen. That equals 0. Let's go to this ion here. We have the dichromate ion. We know oxygen has a -2 oxidation number. We want to know what the chromium is. But remember, in this case here, all the oxidation numbers must add up to the charge on the ion, which is a -2. So we have 7 oxygens with a -2 oxidation numbers, so that gives us a -14. So what plus a -14 will give us a -2? So that's going to be a +12. But we have 2 of these chromium atoms, so the chromium is going to have an oxidation number of a +6 in this compound. Again, all oxidation numbers must add, so we have 2 chromium atoms, each with a +6, that's a +12, and 7 oxygen atoms with a -2, so that's a -14. So a -14 plus 12 is a -2. Again, the sum of the oxidation numbers for an ion must equal the charge on that ion. Let's take a look at this one here, perchloric acid, and notice we have 3 different atoms. So we know oxygen is a -2. We know the hydrogen is a +1. So what we need to know is the oxidation number of the chlorine. So let's take a look here. We have 4 oxygen atoms of a -2 plus 1 hydrogen, that's a +1. So we have a -8 plus 1, and that's a -7. So what plus a -7 will equal 0? 0 because this is a neutral compound. So what plus a -7 is 0? That's a +7. So the oxidation number for the chlorine is a +7. Let's take a look at this. This is sodium permanganate. So we know that sodium is a +1. Oxygen is a -2, so we have to determine the oxidation number of the manganese. So what we have here is we have a +1 plus a -2. We have 4 oxygen atoms. Multiply that by 4. So a -8 plus 1 is a, -7. So the manganese then would have to be a +7 oxidation number. Those all add up to 0. So practice your oxidation numbers. So let's see, how do we identify redox reactions? Well, easily. In a redox reaction, the oxidation number of a species changes during the reaction. Again, oxidation occurs when the oxidation number increases. That's an electron loss. Reduction occurs when the oxidation number decreases. That's an electron gain. Oxidation and reduction occur simultaneously. You cannot have one without the other. Where there's an oxidation, there is a reduction. If you have any species that is oxidized or reduced in a reaction, that reaction is a redox reaction. So some examples of redox reactions. These are easy to see. It is oxidation reduction because right away we can see we have a copper on this side. It has a 0 oxidation number. On this side it has a +2. So copper here has been oxidized. This is what we call a displacement reaction. This one here, we can see right away that it is a redox reaction. So many displacement reactions are redox reactions. Combination reactions, that's where you have 2 reactants to produce 1 product, okay? This is a redox reaction. We can tell here we have oxidation numbers of 0 on the sodium and chlorine. Here, +1 on the sodium and a -1 for the chlorine. So This is oxidation reduction. And all combustion reactions are also redox reactions. Okay, here you have oxygen with a 0 oxidation number, and here of course it's a -2, and the same with water, it's a -2. So oxidation reduction. Remember, combustion reactions produce carbon dioxide and water. This is where an organic compound is burned in oxygen. Okay, complete combustion anyway will produce carbon dioxide and water. Then we have decomposition reactions, and this is where one reactant decomposes into 2 or more products. This triangle here should be above the arrow, and that triangle means heat. So in other words, we heat this substance here, and it decomposes to these 2 substances. Those are examples of displacement, combination, combustion, and decomposition reactions. These are examples of redox reactions. Here's another redox reaction. This reaction is between solid magnesium and copper 2 ion to produce magnesium ion and solid copper. Basically, we have this graduated cylinder here. It has blue copper 2 sulfate solution. We also have this magnesium wire in the solution. And basically what's happening is electrons are being transferred from the magnesium to the copper 2 ion. And so magnesium is losing electrons. The copper 2 ion is gaining electrons to form solid copper. Copper metal here is deposited to the wire, and the magnesium goes into solution as magnesium ion. Let's take a look at this a little more closely. So we have solid magnesium and copper 2. So we can divide this into 2 half reactions, the oxidation and the reduction. Let's see here. Magnesium here has a 0 oxidation number. Here it's a +2. So the oxidation number is increased, so it has been oxidized. The copper goes from a +2 to a 0. Oxidation number is increased, has decreased, so copper 2 has been reduced. The oxidation reaction is the magnesium solid to magnesium ion. And we put the 2 electrons here to balance that charge, okay, on both sides. Both sides of the equation, the charge must be balanced. So the reduction reaction then is the copper ion, and that goes to copper solid. Okay, so the copper ion is reduced to copper solid. Obviously, something causes an oxidation, something causes the reduction. We call those reducing and oxidizing agents. So the reducing agent is a substance that's been oxidized. In this case, the magnesium acts as the reducing agent because itself is oxidized. The oxidizing agent is the substance that has been reduced. So the copper 2 ion acts as the oxidizing agent. It causes the oxidation because it has been reduced itself. Again, an oxidizing agent causes the other substance to be oxidized while it is reduced, and a reducing agent causes the other substance to be reduced while it is oxidized. So let's go ahead and take a look at this equation here, and let's figure out which is the oxidizing agent and which is the reducing agent. Okay, let's take a look at the nitrogen tetroxide. The oxidation number, let me erase this real quick here. There we go. It was in my way. The oxidation number for oxygen is a -2. The oxidation number for the nitrogen, well, let's see. We have 4 negative 2's. That's a negative 8. So that'll be a plus 8 divided by 2. The nitrogen here is a plus 4. Okay, let's do this one as well. Hydrogen has a plus 1 oxidation number. And here, the oxidation number of the nitrogen, we have 4 plus 1's. So that'd be a plus 4 divided by 2. That'd be a negative 2. Okay. Here we have nitrogen in its elemental form. That's 0. For water, hydrogen has a plus 1, oxygen a negative 2. So we see there's no change in the oxygen, but there is a change in the oxidation number for the nitrogen. So here we have nitrogen going from a plus 4 to a 0. Okay, so that means that the dinitrogen tetroxide has been reduced. And then here, our nitrogen goes from a negative 2 to 0. Okay, so what we see is an increase in oxidation number. So the hydrazine has been oxidized. The reducing agent is that which was oxidized. That's the hydrazine. And the oxidizing agent is that was reduced. So that's the dinitrogen tetroxide. So practice some of those equations. Be able to tell what has been oxidized, what has been reduced, what is the reducing agent, which is the oxidizing agent. Now, it turns out the redox equations must be balanced according to both mass and electric charge. Your book shows in chapter 4 how to balance these equations using oxidation numbers, and that's fine. I'm going to show you how to balance these redox reactions using the half reaction method. Let's go ahead and take a look at this. It turns out that in acidic aqueous solution, permanganate ion will oxidize iron 2 ion to iron 3 ion. So notice here, this is not balanced. I mean, we're fine in manganese and we're fine in iron, it's balanced, but we have oxygens on this side and none on this side. And also on this side, our charge is a plus 5. On this side, it's a plus 1. So we're not balanced in charge or in atoms. What we have to do is account for oxygen. What we can do is we can put 4 waters on the right side, and then we can put 8 hydrogens to balance the hydrogens on this side. And that works very well. Now, on this side of the equation, the net charge is, we have a negative charge plus 2, that's a plus 1. Plus 1 plus 8 is a plus 9 charge. On this side, it's a plus 5. We need to be able to balance for the charge. So our main goal right here is going to be to identify oxidation reduction reactions, balance redox equations, either by inspection or by the half reaction method, which is what I'm going to show you, and be able to determine if a redox reaction is properly balanced. In most cases, like combustion reactions, we can balance them using our normal methods. But this one's a little different because, again, we have oxygen on this side and no oxygen on this side. I'll show you how to balance an equation using the half reaction method. You'll learn this again also in general chemistry too. We can balance redox reactions 2 ways, in acidic solution or in basic solution. All right, so what we're going to do here is, these are the rules or the how you go about balancing these redox reactions in acidic solution. So you need to assign oxidation numbers to each atom so we know what's been reduced and oxidized. We split the skeleton equation into two half reactions. We balance all the atoms except for oxygen and hydrogen. We balance the oxygen atoms by adding water to one side, balance the hydrogen atoms by adding hydrogen ion to one side. We balance the electric charge by adding electrons to the more positive side. And then we combine the two half reactions to obtain the final balanced redox equation. How do we do that? We multiply each half reaction by some factor such that when the half reactions are added, we'll see a canceling out of the electrons. We cannot have electrons appear in the final equation. And then we simplify the equation by canceling species that appear on both sides, and we reduce our coefficients to the smallest whole numbers. And then finally we check to make sure that the equation is balanced. So we're going to use the half reaction method. Okay. So we are going to work with this equation here. And let me bring this down a little bit so that I can put the oxidation numbers in. And I'll move that down. Good. That'll be better. So let's go ahead and see what's oxidized and what is reduced. So this part here is easy. Iron goes from +2 to +3. There's an increase in oxidation number, so it is oxidized. And here the manganese goes from, let's see, we have a negative at +7, and here it is a +2, so we see a decrease in oxidation number, so this permanganate has been reduced. Okay, let's write the half equations. Let's do the oxidation first. Here we have iron 2. You know, let me move that over a bit. This is not going to work well here. Okay, let's do this. I'm going to move this over. So here we have, let's write the first half reaction. This is the oxidation. So we have the iron 2, and that goes to iron 3. We look at this and we say, okay, is this balanced? Yeah, the atoms are balanced, but what we have to do is we need the electrons. We have to balance the charge. So I have a +2 charge here, a +3 here. So what I'm going to do is add 1 electron. Okay, so that's good. That half reaction is great. Now let's do our reduction reaction. And the reduction reaction, we have permanganate. Okay, and let's see, we have permanganate. That goes to manganese +2. All right, so manganese is balanced. The only problem is we have oxygen on this side and no oxygen on this side. So on this side, we have 4 oxygens here. I'm going to put 4 waters here. And I have to now balance hydrogen. So I'm going to put 8 hydrogens here. And let's see. We put electrons on the left side. Okay. So let's see. The manganese has gone from a +7 down to a +2. So that's 5 electrons, okay, that have been transferred. So what I'm going to do is I'm going to add those electrons right here. So 5 electrons on this side, okay? So I'm balanced in charge and I'm balanced in atoms here, okay? So now I'm ready to add my 2 equations. I need to make sure that I multiply one or both of these by some factor that'll give me the same number of electrons for both of these reactions so that they cancel out when I add them. So what I can do is I can multiply, well, this here I have 5 electrons, so I can multiply this, the coefficients here, through by 5. So I'll put a 5 there, a 5 there, and we'll go ahead and change this to 5 electrons. Okay, now what I can do is I can add my equation. So let's add the reactants here. Note here that my electrons cancel out. So I have 5 plus iron 2 ions plus permanganate ion plus 8 hydrogen ions. And then on this side I have 5 iron 3 ions plus manganese 2 ion plus 4 waters. And I go check, I have 5 iron, 5 on this side, 1 manganese, 1 manganese. I have 4 oxygens, 8 hydrogens, and 8 hydrogens. This is balanced. So we balance that in acidic solution. Now, when we balance in basic solution, we do the above, but we add 2 more rules. What we do is note the number of hydrogen ions in the equation, and then we add the same number of hydroxide ions to both sides of the equation. We then can simplify the equation by realizing that hydrogen ion reacts with hydroxide to give water. So we combine those, and then we cancel any waters that occur on both sides of the equation, and then reduce the equation to the simplest terms. Here is an equation. I'm going to follow what I did in this for this first reaction. I'm going to find out what's been reduced, what's been oxidized, and I can write my 2/2 reactions. Again, this is in basic solution. I noticed this here, it talks about permanganate ion. I think I had a different equation here before, so just get rid of that. Okay, because that doesn't correspond to this. So here we have sulfide ion has a -2 charge, and here we go to sulfate ion, and the sulfur here has a positive, let's see, we have -8. What plus a -8? That's a +6 oxidation number for the sulfur, +6. So it goes from a -2, it increases to a +6. So this here is our oxidation. And then we have iodine. This is molecular iodine. That's a 0 oxidation number. Here we have a -1. So the oxidation number is decreased. So this is the reduction. So let's go ahead and write the 2/2 reactions. I'll do this first one here. It's a little bit easier. So I have iodine, and that goes to iodide. And again, this is the reduction. We go from 0 to a -1. And what I need to do is I need to balance what I have here. So I have the 2 iodides here, and let's go here. I'll put the electrons here on this side. So I'm going to need, so we're going from 0 to a -1. Here I'm going to need 2 electrons. Okay. And let's go ahead and write the other half reaction. So we have sulfide ion. It's going to sulfate ion. And let's go ahead and put 4 waters on this side. and we need the 8 hydrogens on this side. Okay, and let's see, what else do we need to do here? Here we go from a -2, and the sulfur here is a +6. A -2 to a +6, that means that I need 8 electrons. Okay, so, okay, because we're going from a -2 to a +6, so that's going to be 1, 2, plus the 6, 8 electrons. We'll put that on this side. So let's see, I think we have everything we need here. We're balanced in charge, and we're balanced in the number of atoms. So here I have 8 electrons, here I have 2 electrons. I'm going to multiply this through by 4. Okay, so what we'll have here is 4 of those. That'll give us 8 electrons, and 2 times 4, that's 8 of these. These are balanced in both charge and the number of atoms. We can now add the equation. Our electrons do indeed cancel, and we have 4I2 plus sulfide ion plus 4 waters, and we have sulfate ion plus 8 hydrogens plus 8 iodides. Okay, so we want to get rid of the hydrogen ions here, so I'm going to add, I have 8 hydrogen ions here, I'm going to add 8 hydroxide ions, and I'll have to also add them to this side. I can combine the hydrogens with the hydroxide ions for 8 waters. So let me rewrite this here. So we have our 8 hydroxides plus 4I2 plus sulfide plus 4 waters, and plus 8 water molecules plus, what am I missing here, 8 iodides. Now we have 8 waters on this side and 4 on this side. I can subtract 4 waters from both sides, and our balanced equation will be so this is our balanced equation. Again, check to make sure it's balanced. It is. So that was how to balance these in basic solution. So you can see here, I have this chart for group 5, 6, and 7A nonmetals there. And you can see here that, for example, nitrogen, depending on the compound it's in, it can have many different oxidation numbers, anywhere from a -3 up to a +5. The species, like for example here, when nitrogen has a +5 oxidation number, it can only act as an oxidizing agent. Okay, in this case here, where it's a -3, it can only act as a reducing agent. These in between here can act as either oxidizing or reducing agents depending on the reaction. Take a look at this in your book. So, you know, we have so many compounds here. We have the nitrate ion, nitrogen's a +5. Dinitrogen pentoxide, nitrogen's a +4. Nitrite ion, nitrogen's a +3, and so on. And the same goes for some of the other non-metals. Remember, a reducing agent is itself oxidized. And what do we know about something when it's oxidized? Well, we know that it loses electrons. So metals, we know, lose electrons. But metals do not all have the same tendency to lose electrons. In other words, Some metals lose electrons more easily than others. We know then that because metals are oxidized, they act as reducing agents. And the power of the reducing agent can vary greatly. Atoms of groups 1A and 2A, they lose electrons very easily, and they are very good reducing agents, okay, because these atoms are readily oxidized to metal cations. There are other metals that are oxidized with more difficulty, and therefore they are poor reducing agents. So this is where the activity series of some of the metals come into play. In this activity series, we see that the metals are ordered according to their strength as a reducing agent. At the top are stronger reducing agents than those towards the bottom. So the reducing power decreases from top to bottom. So we compare, for example, copper and cadmium. We see that cadmium is a very good reducing agent. And what it means is it loses more, or it loses its electrons more readily than does the copper. You don't have to memorize this. I would give you this on an exam. Okay. From this table, we can see the different metals vary in the ease with which they are oxidized. For example, zinc is oxidized by aqueous solutions of copper, but silver is not. Okay, that's because silver is poor reducing agent. So zinc is easier to oxidize than is silver. Again, the metals at the top of this list are more easily oxidized, and they react more readily to form compounds. A lot of these metals at the bottom of the activity series, such as silver and gold, again, these are very poor reducing agents, and they lose their electrons less readily. These metals are used to make coins and jewelry, and we call them the noble metals. That's because they're not very reactive at all. So we can use our activity series to predict the products of reactions between metals and metal salts, or metals and acid. Any metal on this list can be oxidized by the ions of the elements below it. Copper metal can be oxidized, here we have copper, by silver ions. Okay, and we can write the equation. Do I have it here? No. So we can write the equation like so. We have solid copper plus silver ions, that's aqueous, to give us copper 2 ion plus solid silver. Okay, so copper metal is oxidized by silver ions. The oxidation of copper to copper ions is accompanied, as you can see, by the reduction of the silver ions to silver metal. If we were to put some copper wire into some silver nitrate solution, we could see that the color of the solution would turn blue, which would be due to the copper ions, and we would see the silver deposited on the copper wire. It almost looks like tinsel on a Christmas tree. Now, metals above the hydrogen in this activity series, so these metals here above the hydrogen, are able to react with acids to form hydrogen gas. So nickel will react with hydrochloric acid in order to produce hydrogen gas. Elements below hydrogen in this activity series are not oxidized by hydrogen ion. So that means, for example, copper would not react with hydrochloric acid. That gives you an idea of the strength of reducing agents. Let's take a look now, the last part of this, at titration. We've talked about acid bases, reactions. We're going to talk now about titration. In a titration, we determine the amount of a substance by adding a carefully measured volume of a solution that has a known concentration until the reaction of the two is just complete. Titration is a volumetric analysis. Volumetric analysis is the method of analysis based on titration. Usually what we want to do is find the mass, the number of moles, the percent of the analyte in a sample, or its concentration. So what we're able to do is measure the precise volume of a titrate needed to completely react with the analyte. We do that using a burette. We can read to the hundredths place. And then titrant is put into the burette. The other reactant is placed in a flask. We usually add a few drops of indicator so that we can see the color change when the reaction is complete. So the equivalence point in a titration occurs when the titrant completely neutralizes the analyte. In other words, the reaction is complete. This is when the analyte and the titrant, the analyte is the substance that we want to determine the concentration for. So the equivalence point is when the titrant and the analyte have been brought to their stoichiometric proportions. So that's according to the balanced chemical equation. So what you do is you add the titrant slowly to the contents of the flask. Once the indicator changes color, this is the end point. That means all of the analyte in the flask has been reacted. The end point is a little bit past the equivalence point. Okay, not much, but a little bit. So from the balanced analytical equation and from the amount of titrant we used, we can determine the concentration or the amount of the analyte present. And we can report that again in as mass, as percent, as moles, however we are asked to report that. So let's take a look and see how we do these. Okay, here's an acid-base titration setup. Let's say you're doing an acid-base titration. There are different types of titrations, by the way. There are redox titrations, precipitation titrations, and so on. But basically for this acid-base titration, you would go ahead and measure out a portion of the acid solution, and we place that into the flask, put a couple of drops of indicator in there, and then your base, you would know the concentration. You would add that to the flask from the burette until you see the color change, till that end point. Again, as I said, that end point is a little bit past the actual equivalence point. We are going to learn how to do some of these calculations. We've done these before. They're nothing new. Basically, we are going to be working the problems using the stoichiometric coefficients to determine the mass of a sample. Call this volumetric stoichiometry. Again, we can do these calculations for acid-base, precipitation, redox, and many other types of volumetric analysis. What you have to remember is that the objective of the titration is to determine the number of moles, the number of grams, the percentage or concentration of the analyte. This is the substance that you need to determine the concentration of. So let's do a little problem here. Here we're asked, we have a problem. What volume in milliliters of 0.245 molar sodium hydroxide is required to neutralize 25 milliliters of 0.1026 molar hydrochloric acid? First thing you need is your balanced chemical equation. And the only difference between this and the other problems we've done is we are using solutions. First thing we need to do is find out the number of moles of HCl and sodium hydroxide. So here we're asked, another thing we need to remember is the molarity is equal to the moles of solute over the liters of solution. We're going to be using this a lot. Here we're asked how much of this 0.245 molar sodium hydroxide is required to neutralize 25 milliliters of 0.0126 moles of hydrochloric acid. What we need to do is find the moles of sodium hydroxide. Once we do that, we can use its molarity and the moles to find the volume. First thing I'm going to do is determine the number of moles of hydrochloric acid. So we know that molarity times volume will give us the number of moles. So my volume, my molarity is 0.1026 moles per liter of hydrochloric acid. And we'll multiply that by the volume. And of course, we have to convert 25 milliliters to liters. That'd be 0.025 liters. And then let's go ahead and determine the number of moles of that acid that is reacted. So we have 0.1026 times 0.025. And the number of moles is 0.002565 moles of HCl. So that is how much is reacted. Okay. Now, from our stoichiometric coefficients, we know at the equivalence point that 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid. So let's determine the moles of sodium hydroxide that is needed to react. So we have 0.002565 moles of HCl. See, we use the equation stoichiometry. From that, 1 mole of HCl reacts with 1 mole of sodium hydroxide. So because of the 1-to-1 ratio, what we have is 0.002565 moles of sodium hydroxide reacts. Well, it asks me what volume do I need of this molarity. Well, I go up here and I realize that the volume is going to be equal to the number of moles divided by the molarity. So the volume is going to be the number of moles, so the 0.002565 moles of sodium hydroxide divided by its molarity, 0.2450, and that's going to be 0.002565 divided by 0.245. I get 0.01047 liters. We want that in milliliters because that's what they asked for. So that would be 10.47 milliliters. So again, we're doing the problem the same way as before using our balanced chemical equation, but we have to do one step further. We have to determine the number of moles from the volume and the molarity. And then we compare those. We use our mole ratio from our balanced chemical equation, and then we were able to use this in order to determine the volume that was needed. Here's another problem that we're going to do. Here we're told that the quantity of chloride in a municipal water supply is determined by titrating the sample with silver ion. Here is the precipitation reaction. The end point of the titration is marked by a change in color of a special type of indicator. Yeah, we actually use dichromate ion, but I won't go into that. So here we're asked how many grams of chloride ion are in the sample of water if 20.2 milliliters of 0.1 molar silver ion is required to react with all the chloride in the sample. And B, if the sample has a mass of 10 grams, what percent of chloride does it contain? What is our plan here? Well, let's do part A. What we can do is we need to determine the moles of silver ion that have reacted. And we can do that. Again, we know that molarity is moles over the volume in liters. So if we multiply the molarity times the volume, we'll get the number of moles. So let's go ahead and do that. So moles of silver ion will be the volume. We have to convert this to liters. 0.0202 liters times the molarity of the silver ion. That's 0.100 moles per liter. And what we get is, here we get 0.00202 moles of silver ion. Now, from the balanced equation, again, you have to always go back to the balanced equation. And we see that 1 mole of silver ion is equal to 1 mole of chloride ion. So there's a 1-to-1 mole ratio there. Let's go ahead and determine, we're asked how many grams of chloride ion are in this sample. So let's start with 0.00202 moles of silver ion. Okay. And let's go ahead and use our equation stoichiometry to get from moles of silver ion to moles of chloride ion. And then use the molar mass of chloride. So 1 mole of chloride is 35.5 grams of chloride ion. And that gives us 7.17 times 10 to the negative 2 grams of chloride ion. Okay, so that answers part A. So what about part B? Well, what we want to do is calculate the percentage of chloride in the sample. So we need to compare the amount of chloride in the sample with the original mass of sample, which we were given in the problem. So we have 7.17 times 10 to the negative 2 grams of chloride ion in 10 grams of sample. Multiply that by 100, and that's going to give us 0.717% chloride ion in that sample. So these are the types of problems we can do. Anyway, we're finished here with chapter 4. Practice these calculations, these volumetric, stoichiometric calculations. And if you have any questions, let me know. Everybody have a great day. Talk to you next week.